Hey there everybody, in this video we are going to be kind of tying things together with regard to the unit circle, radian measure, and arc length formulas, things that we've discussed in previous videos. When we're doing this, I'm frequently going to be referring to the unit circle. So if you do not have the unit circle memorized, which a lot of us probably don't, that's okay, or if you don't have access to it, here you go. So if you need to take a picture of this or screenshot it, what have you, please feel free. You'll notice on the unit circle we have our degree measures, we have our radian measures, so the radian measures have the pi, and then within the coordinate parentheses we have cosine and sine values. So cosine, comma, sine. All right, so let's get into finding the tangents of certain angles from the unit circle. Well, if I know that the sine of a function is the opposite over hypotenuse, and the cosine of a function is adjacent over hypotenuse, what I could say is that the opposite over hypotenuse divided by the adjacent over hypotenuse, since the hypotenuse is in the denominator of both of these fractions, they'll essentially nullify one another. So if I took the ratio of sine over cosine, opposite over adjacent, that would be the tangent. So the tangent of any angle is equivalent to the sine divided by the cosine. When we're talking specifically about the unit circle, it's going to be the y-coordinate divided by the x-coordinate. So the second divided by the first. Now a few things to take note of when we're doing this. First, anytime my x value is a 0, so here at 90 or at 270, I'm going to have an undefined tangent value, and the reason for that is we can't divide by 0. If you try to divide by 0, the whole universe will implode in on itself, and everything you've ever known or loved will then cease to exist. If we are finding the tangent ratio for the 30, 45, or 60 reference angles, and they'll repeat over and over and over, it's always going to be the second value divided by the first, but I'm noticing both of these fractions have 2's, and that's going to hold true. The denominator for all those fractions is going to be over 2. So really, I only care about the numerators because those denominators of 2 will kind of negate one another. So here's the first quadrant, but I'm going to be dragging along this unit circle as we go through, so won't be needing that. All right, well, let's see what we got. Tangent of 5 pi over 4. 5 pi over 4, where are you? 5 pi over 4, bam. So it's going to be the second numerator divided by the first numerator. So negative rad 2 over 2 over negative rad 2 over 2 again. Since these denominators have the same value of 2, we can essentially ignore them and think of this as negative 2 over 2 over, or sorry, negative rad 2 over negative rad 2. Well, that's just the same value being divided by itself, right? So anytime that happens, we get 1. Little life hack. Any tangent on a 45-degree reference angle, so anything that has a denominator of 4, will always have the value of 1 or negative 1. All right, next up, tangent of 135. 135 is right here. So negative rad 2 over 2 over rad 2. So negative rad 2 over rad 2. This will be a negative 1. Tangent of 2 pi. 2 pi is right here. Second number divided by first. 0 divided by 1. Well, 0 on top is okay. So the quadrantal angles here for tangents will either produce zeros if it's a 0 degrees or 180, or if it's a 90 or 270, it would produce an undefined value. Let's see what we have down here. Tangent of pi halves. Well, that's 90 degrees. That would be 1 over 0. We cannot divide by 0. So this would be undefined. Tangent of 120. Second numerator divided by first. Rad 3 over negative 1. Well, that's just negative rad 3. Tangent of 7 pi over 6. 7 pi over 6, here we are. Nope, there, nope, where'd you go? There it is. Second divided by first, negative 1 over negative rad 3. Well, the negatives cancel out, so there's really a positive 1 over positive rad 3. And I'm really not too thrilled about having that rad 3 in the bottom, so I need to rationalize. This would be rad 3 over 3. So any 30-degree reference angle, so anything that has a 6 as the denominator, or is 30 degrees away from our x-axis, we'll always have a tangent value of rad 3 over 3, or depending on the quadrant, maybe a negative. Any 60-degree reference angle will be a negative rad 3. Any 45-degree reference angle will be a 1 or a negative 1. 0/180 is going to result in a 0. 90/270 would be an undefined. All right, let's carry this along. I don't know if we'll need it anymore, but just to be safe. Next, applications of arc length. So just as a reminder, the arc length formula is S equals R times theta, as long as theta is written in radians. All right, a skateboard ramp is called a quarter pipe. The curved surface is determined by the radius of a circle. Find the length of the curved part of the ramp. All right, so we've got a little skateboard ramp that this guy is riding on. What we want to figure out is, what is the length of that curved part? What is the arc length there? They're telling me that it's 90 degrees. And since I'm thinking ahead, I know that I need radians. That's pi over 2 radians. The radius of this circle is going to be 8. And yes, I realize it can be confusing having radius and radians. So if I'm finding the length of that arc, I'm taking the radius, 8, and multiplying that by the radian measure, pi over 2. And that's going to give me 4 pi feet. 4 pi feet. Now, hypothetically, if they wanted this to be in decimal form, if we're actually trying to calculate this, we'd go straight to our calculator and actually type in 4 times pi. So we type in 4 times pi and then just round to a few decimal places if it requires it. So that is roughly 12.57 feet. Not too shabs. All right, onward. Next, we have an image of a clock. Yay! How many degrees does the minute hand, so the minute hand of a clock is going to be the longer one, travel from 3 o'clock to 3:40? Well, at 3 o'clock, the minute hand is going to start right here. And then each number here represents 5-minute intervals, in case we forgot how to read analog clocks. 3:40 is going to happen right down here. Now, there are a few ways to think of this. What I need to know is, let me draw in some angles here. What is this angle measure there? I know that it's gone past the halfway mark, so it's going to be more than 180. But I need to know, what is the total theta? And thankfully, we're talking degrees. So here's a few ways you could do it. Method number 1, set up a proportion. Okay, if we went 40 minutes out of a total 60, because 60 is 1 lap around in an hour, I could say, how many degrees is that out of a full rotation of 360? That's one method. Or I could say, hey, we've traveled 1, 2, 3, 4, 5, 6, 7, 8 numbers. So we've gone 8 numbers out of the possible 12 numbers on a clock. Set that equal to how many degrees out of 360 is that? Here's the way I personally like to do it, though. If I know there's 360 degrees in a clock, and there's 12 numbers, well, then I can make the claim that each number is 30 degrees. So if I know that each little number represents 30 degrees and I've gone 8 numbers, I'm going to get 240 degrees total. If you chose to do it this way with either proportion, you would still get the exact same result. Because what happens here is these ratios we have, they're both going to simplify down to 2/3. And you're just finding what is 2/3 of 360, that would be 240. So multiple ways we could do that. Next one, the minute hand of a clock is 5 inches long. How far does the minute hand travel from 1 p.m., so it's going to start here, to 1:25 p.m., so it's going to end on the 5. Round to the nearest tenth. So they're asking us how far is that distance, which means I need to use my arc length formula, and fortunately they already tell us the radius would be 5. What I don't have is that theta. So I could do what we were just talking about. I could say 5 out of 12 is x over 360, or we could talk about minutes. I could say 25 over 60 is equal to x out of 360. But me personally, I like to think of each number as 30 degrees. So that's 30, 60, 90, 120, 150, 150 degrees. So I've traveled 150 degrees. But we need that in radians. So to convert 150 degrees into radians for this arc length formula, I would do 150 times pi over 180, and then just reduce down 15 over 18, or 150 over 80. They can both reduce down by a factor of 30, so I get 5 over 6. If you're still confused on that, you could refer back to our unit circle and say, okay, 150 degrees, that's 5 pi over 6. So we just found our theta, 5 pi over 6 radians. This thing works out to be 25 pi over 6, and what were our inches, or units were inches. Now if the problem asks us to round, and it does, if it asks us to round, that means we're going to have to punch this into our calculator. So 25 times pi, and then divide that all by 6. Let's see if I can get that on my calculator here. I'm getting 13.1 if we go to the nearest tenth. There we go. All right, that is it. That is all for this video. You know the drill. If you have any questions, please let me know. And as always, good luck, have fun, be safe, roll tide.